Not yet. The slides will be online. We'll put these slides online, but I'm going to do a demo, and this demo hasn't been written down anywhere yet, so. Notes, a lot of notes. Demo is definitely new. Since I came up with it like an hour ago, so. Okay, we'll start in about 1 minute. Hands up if you've used eBPF so far. Awesome, so that's about a third of the room. What about ftrace? Hands up if you've used ftrace. That's actually more people. It should make Stephen happy. Stephen's giving a talk tomorrow morning on ftrace, which would be really good. I use both tools. I happen to be talking about eBPF for the next hour. Okay, thanks for choosing this talk. My name is Branden Gregg. I am a senior performance architect at Netflix. And as of tomorrow, I'll have been at Netflix for 5 years. Time flies. That means I'll have worked on Linux full-time for 5 years. When I came to Netflix, I was a dtrace expert and performance analyst. And coming to work on Linux full-time, I knew that I'd have a challenge of lacking all of the tools that I created. But I knew this challenge would also motivate me to find out new ways to accomplish things. And I discovered early on that Linux had ftrace. And so early on at Netflix, I created a suite of tools called perf tools that were based on ftrace, and they let me solve a lot of problems. I also met Alexei Storytoyov, who was working on a new virtual machine for the kernel called eBPF. And I saw how that could be used to do more programmatic things. And so I've also created a lot of tools using eBPF. And so now 5 years on at Netflix, I finally do what I want to get done in production using all of these new tools. It's really amazing and exciting. And also we're at the point with these technologies where early on we made sure that they got into the kernel because that takes a long time to propagate. And now we're getting them packaged. And so I was swapping emails with Canonical yesterday to make sure the BPF trace package appears for the Ubuntu distributions, which would be really awesome. They've already created a snap for it. And we have BCC, which is the other front end, has been packaged. So we're at the point where these superpowers, you can use them for analysis just by doing a package add to a system. But what I want to start with is a live demo. And often in talks, we come up with these nice canned demos where everything works and it's all sunshiny. And myself and Martin, we've been doing these demos where it's like, we want something more gritty. We want something realistic. Something where it's not like a 10-line program that we're debugging. And so we thought, why don't we just like fire up Minecraft and then do performance analysis of Minecraft? It's going to be fairly complicated. And so I started this an hour ago to see how far I would get. So my demo is using eBPF for performance analysis of Minecraft. Is anyone in the room who has worked on the Minecraft source code? A developer from Mojang? Yes. Open source, yes. Well, yeah. All right, so you might be able to help me out. No, I'm serious. I am actually going to use eBPF on Minecraft. Right. So here's Minecraft. Hands up if you've played Minecraft. Okay, so about as many people as ftrace. So that's pretty good. I tell you what, between Minecraft and ftrace, I don't know which is more fun. I'm a performance engineer and I love ftrace. I'm certainly better at ftrace than I am at Minecraft. So I've created this world called SCaLE 17x. And the arrow keys don't work because I have to press W and things, okay? Okay, so Minecraft is working. Now what I'll start by doing is, so there's a couple of front ends for eBPF tools. One of them is BCC for the BPF compiler collection. We've been working on that for many years now. And the other is BPF Trace, which is newer. They're complementary. BCC is really good for having all these canned tools that do one thing and do it well. So I'm going to use Profile, which is nice and simple. In fact, it's in my path anyway. Profile is a CPU profiler. It can sample stacks at a timed interval. And Minecraft is running. How many Javas do we have? Just one. Okay. Minecraft happens to be a Java application. Hands up if you've done performance analysis of Java. Okay, it's actually pretty hard because Java is a jittered runtime and the compiler is constantly moving things around and you don't have a symbol table. This is the exact type of gritty, horrible thing that Martin and I were interested in doing a demonstration of. So this is where things actually don't work out well when we start doing performance analysis, and that can teach us more about how things work. So I'm going to do profile of, say, 99 hertz. In fact, even though I wrote the tool, I do forget all the switches. I want to do, I'll just do the process ID. I know, dollar, whatever. Okay, so back to playing some Minecraft. And here's my stacks. Did miss some. Some stacks I can translate. So this is C2 compiler thread. But a lot of stacks it can't. So there's all these unknowns, unknowns, unknowns. And they look a bit broken. Anyone know what's going wrong? Multiple things are actually going wrong. What's one of the things that's going wrong? I'm missing symbols? Yeah, that's one thing. What else? Stacks should not be one frame deep, usually. So BPF runs in kernel context with interrupts disabled. It's a very dangerous context to run in. You don't want to do anything really CPU expensive, and the BPF verifier will check and reject programs that do anything too dangerous. The stack walker that we have in BPF right now is a frame pointer based stack walker. And so that's where the conventional frame pointer register, which is RBP on x86-64, saves the location of the previous frame. And so it's very simple. It's just a linked list. I can read the frame pointer register, RBP. It tells me where the next one is on the stack. I can read that. And at a known offset, +8, I can fetch the return instruction pointer. So by walking a linked list and then referencing the +8 address, I have a stack trace. And the stack trace shows me the flow of code. Stack traces are great. It teaches us what's going on. Here I'm doing CPU profiling using Profile, a BCC tool, using BPF. It's sampling at 99 hertz on all CPUs. It's walking the stack trace using the frame pointer. And for efficiency, it is frequency counting the stack traces in kernel context. The output that we see here, it says, I saw this entire stack trace 8 times. Most profilers prior to BPF will emit these samples to a log or a file. So if you've used the Linux perf utility, it has the binary perf.data file. Now, over the years, they've done a lot of optimizations to perf.data, and Stephen can explain them better than I can for how we get the data written out. But you still have to write out an entry for every sample. With BPF, the kernel will do a hash of the stack trace, and if it's seen it before, I can just increment a counter. I don't need to keep writing these samples out. So it all summarizes in kernel memory where it's very efficient and cheap, and at the end of my profile, it then dumps out the frequency counts. So this is a new generation of CPU profilers. CPU profiling at Netflix, this is what we use all the time to understand our code. It's a really important performance analysis tool, and with BPF, we're actually making it much more efficient, which is exciting. CPU profilers, by the way, have been around for decades. So to think that we've just had a major innovation in CPU profiling in the last few years is pretty exciting. So that's great, and this stack trace works. We start at start thread, and then start thread calls thread native entry and so on. We get into the C2 compiler, and we're doing phase idle loop. But a bunch of these are broken. Yeah?
How expensive is doing the caching of stack traces and comparison of the stack traces in the kernel?
So the kernel does have to do the hash comparison of stack traces. I don't have performance numbers. It's something that Alexi's, I'm sure, has put a lot of work into. Alexi's an ex-compiler engineer, so he's very sensitive about cycles and where they've gone. So it's something we could test. But I trust Alexi has optimized this pretty much as far as it can be optimized. Yep, as Stephen said, a quick hash algorithm. Now, what I want to talk about is why these stack traces are broken. Like I said, this is a gritty example of where things go wrong. And you can learn more about when things go wrong than if I just showed you a beautiful, sunny example of things going right. The stacks are broken because the compilers will reuse the frame pointer register as a general purpose register. This came from 2004, and it was a single change to GCC by a contributor who thought it was a good idea for i386. On i386, you had 4 general purpose registers. So if you're able to free up the frame pointer register as a general purpose register, the compiler would go from 4 to 5 registers. So you'd have a fairly significant performance boost for all the software that you compiled. So that makes a lot of sense. But for x86-64, that's a different architecture. We have 16 general purpose registers. Freeing up RBP just gives us a 17th. It's not really worth it. And the problem is it breaks stack traces like this. So why did the GCC developers accept this as the default for compiling? By the way, this is Java, so it's actually this, the C2 compiler has done the same thing, right? They accepted it because as part of the patch suggestion, the developer said, oh, stack walking is a solved problem because the GDB folk have done all this amazing work with dwarf and doing the unwind tables. And so I'm not breaking stack walking by making the frame pointer a general purpose register because everyone's using this fancy dwarf unwind tables for doing stack walking. What they didn't take into account is traces. Traces like BPF, which didn't exist back then. Traces, if you're a debugger like GDB, you can do expensive things. It doesn't matter. You use a level process. When you're a tracer, you're running an interrupt disabled context. So we have to be very careful about the code that runs. And doing the dwarf style lib unwind of stack traces is actually very expensive. And we're not sure we will ever do this in BPF. Like we may never ever code this in BPF. Someone may say, oh, here's a solution. And then the security folk will say, well, there's no way we can accept this because it breaks various security policies in BPF. Linux did come up with a new stack walker recently called awk. By the way, there's a ORC, awk. There's a theme here. So you've got ELF, which is where this comes from, which is the executable linked format. You've got dwarf, which gives us a lot of debug info, and awk is a new stack walker. So awk is smaller than dwarf, although that doesn't make sense now that I say it out loud. Anyway, the awk format is smaller than dwarf, so we've talked about maybe we can do an awk stack walker in BPF, but at the moment we've got frame pointer based stack walkers because interrupt disabled context is expensive when we need this to be fast. So what can we do? I can fix that. So let's go back to Minecraft. Let's get out of this. Now, if it sounds like I'm going on this weird tangent, I'm not. This is exactly what we have to do at Netflix when we're working on production applications. These are the exact issues we run into. It's like stack traces don't work. We need to turn on frame pointers. We need to figure this out. Minecraft, amazingly, has ways you can do custom launches. So I can say, let's do a frame pointer version of Minecraft. And I'll say for the JVM arguments, -XX plus preserve frame pointer. Okay. Oh, there it is. Got that right. Now let's run a frame pointer version. No, don't go full screen. Now, just to be sure. Okay, so it did match something, so I am running with the frame pointer. Okay, so it still seems to be going just fine, even though I just turned on the frame pointer for Java. Now I'll do my profile. Oh. Back to the game. I should mine things, but I haven't figured out what key do I press to mine things. Who knows? Who knows how to play this game? It's the mouse press? Oh, yeah, here we go. Now I'm doing it. I'm mining things. I should have brought my son up to help me do this presentation. My son's 9 years old, 8 years old. So, okay, now things look different. Now when I look at these stack traces, once I get past the compiler, which is busy, so we have these unknowns, okay? This looks much better. Unknown, 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 rather than just having one line and then it stops. The reason why it says unknown is that the location of those frames is in the heap, or it's like some mmap segment. This is where the C2 compiler has compiled methods on the fly and then put them in memory and run them. This is JIT compilation, just-in-time compilation. There, fortunately, is a way to do symbol translation for these. The Linux perf tool came up with it. It's supplemental symbol files. They live in /temp. They're perf-pid.map. And for runtimes like Java and Node.js and various other ones that have JIT compilation, there's usually a way you can dump a symbol table so that perf can read it. There is an open source Java agent called perfmap agent, which can do this for us. And I've written a utility called jmaps, which is on my FlameGraph repo. If I run jmaps, it snapshots the symbol table. So there it is. That's what it looks like. So it's got addresses and then whatever the Java thing was. So by running jmaps, I can then profile it again. And then, okay, now it looks a bit different. So now we're starting to see the Minecraft source code, BNQ, BNV, BNV. If you've seen this sort of thing before, it looks like they've got like some sort of a obfuscation to utility, but sometimes it's not obfuscation. Sometimes it's just for compression. They just want to compress down the symbol names. So there's some sort of compressor or obfuscator, but at least we're actually doing some of the translations now. There's a lot of these interpreter frames as well, and that's because with the JVM, it initially runs methods in the interpreter, and after it hits a compile threshold, it will then compile it and then run it natively. And we want it to run natively because then it has a symbol address and location in memory. In fact, we want it to run natively so much, I'm just going to modify it yet again. Launch options, and say compile threshold equals 10. Did I get that right? It's been a while since I've used it. Compile. Yeah, compile threshold equals, yeah. So now what I'm saying is only after 10 invocations of a method, you should compile it up. Once you've compiled it up, we'll be able to see it. Okay, now if I do my profile. Now I'm going to do a different type of profile because there's a problem with this jmaps in that jmaps takes a snapshot of the state of symbols. So if I run jmaps and then I talk to you for 15 seconds and then I run profile, there is a time in between running JMaps and running profile where the symbols may have changed. And so sometimes symbol translation gets a bit off. I'm going to demo a different tool, BPF trace. And I'm going to write a profiler as a one-liner. Profile hertz 99 if our PID is the positional parameter, uStack, frequency count the user stack trace. Now in the end routine I can do this. Run JMaps, then print out our stack traces, and then clear it. This is great because I can do some custom things. I'm now switching from BCC, which is profile, to BPF trace, which is the new BPF tracer. And it's nice because I'm saying run JMaps immediately before you use that symbol translation to minimize the possibility for churn. Oh, there's a pig. Can I give the pig the grass that I'm holding? No. Okay, let's have a look. So it did the symbol translation. You might have seen it really quickly, and then immediately we printed things out. There should be fewer of these interpreter lines now, but things should be looking better. What I'm going to do is I'm going to turn this into a flame graph so we can see a flame graph of Minecraft. I'll go back to profile. Make sure there's only just one of them. And profile has a -F option to output in folded format. And I want to do it for, I'll just do it. Okay. And then I can take that, I can turn into a flame graph, then open that up in my browser. And I'll go here. Where was I? I was in BPF trace. All right. So now I can see that. Anyone used flame graphs before? Awesome. This is like almost everyone. So I can mouse over and I can see while I was playing, 30% of our time was in the C2 compiler. So you wouldn't have thought it when I was walking around looking at that pig and throwing grass at it, but the CPU time was actually mostly the compiler. And then over here is the stack trace for Java. Oh, I need to merge. These symbols should be joined together. Anyway, let me fix that. Yeah, for some reason there's these extra semicolons the perfmap agent is sticking into things, and I'm just going to use sed to get rid of them. I need a G in there. There we go, much better. So now I can browse this and I can see all the time in Java, and I can quantify it and look for optimizations. It would be more exciting, but they seem to have run it through an obfuscator, so I've just got these characters. Now, so far, that's a neat demonstration of CPU profiling. But BPF gets much more exciting. BPF gets much more exciting than that because we can do off-CPU profiling. We can instrument reads and writes. We can instrument mutex locks and all the other exciting things. So here is an off-CPU profile of Minecraft. So as part of BCC, there's a tool called off-CPU time. It's another tool that I wrote. What this does is it measures the time from when a thread blocks and goes off CPU to when it then comes back on again. And it does that with the stack trace. It's the counterpart to CPU profiling. With CPU profiling, I can browse around and quantify how much time I am spending on CPU and which frames are doing it. So I can see 13% of the time was in LAXY, whatever that is, and there's all the child functions. And so if I'm the developer of the code, this is awesome. If I'm not the developer of the code and I'm an operator or a sysadmin, it's still fairly useful because I can still get some information on that target software, even though I probably don't understand most of the functions. But that's CPU time. I want to know this for off CPU time. If you look at a flame graph for CPU time and off CPU time, that's all of time. That's 100% of time. So it means you can basically take on any performance issue. So I'll do my off CPU profiling. I want pgrep Java. Yeah, let's just do it. Back to the game. Make some more holes. All right, so off CPU profiling, and here we go. There's lots of stacks. So here's some, there's some lambdas happening in get color happening in Minecraft. Okay, so that's interesting. I think the time is in microseconds, so there's 13 milliseconds in total was here for whatever reason. But if you look at a lot of these stacks, something looks wrong. We're back to these unknowns. And if you look closely, a lot of them are over pthread cond weight, or read, or epoll weight, or things like that. Why is the stack broken now? I thought I fixed the stack traces. Anyone tell me why they're broken now? Again, we've hit this in production at Netflix. This is why I wanted to demonstrate this. This is an excellent simulation of the greediness of real-world analysis. It's broken because epoll weight and pthread mutex lock and all of those come from libc and libpthread, and they're compiled with emit frame pointer, the GCC default. So even though it's only one frame deep, you're walking down from kernel context, you go into libpthread, and it's like a black hole. It like sucks up the frame pointer, and you can't go any further. And so I'm missing the rest of the stacks. How am I going to fix this? Well, let's do this again. Go back to my launch options. So here's something I made earlier. It's Java with, so it's user bin java dash whatever, and it does an LD preload of versions of libc and libpthread that I compiled earlier with the frame pointer, and then it goes and runs Java. So I've done my own compilation of those libraries, and I called this wrapper java-libc frame pointer, and Minecraft is awesome. Like, you can just tune this stuff. So the Java executable is my version, java libc frame pointer, and then save that. Okay, so now let's play Minecraft. I'll get my profile ready. Okay, look around. Okay, it's better. So actually, I need to run JMap, so I forgot to run JMap. So now we're able to go. So here's an example here, VM periodic task. Normally, we'd stop here, pthread cond weight, because libc would throw out the frame pointer and you couldn't go any further. Now I can keep going. I can see that came from OS platform event, monitor IO weight, and so on. Watch a thread sleep. And so now I've fixed those stacks as well. And now for the final Minecraft demo, I can do, this is a flame graph. Okay, back to the game. Dig in some holes, I guess that's what you do. Now I can do, okay, that looks good. Remember that sed thing I did earlier? I probably need to do that as well. I should fix perf map agent. Now I can feed it into flame graph. I'm going to change the background color because this is an off CPU flame graph. It's not a CPU flame graph, and I want that as a visual reminder. Okay. All right. It translate? Nice. Let me make that font size a bit bigger so you can read it. Okay, so now if I browse across, this is off CPU time. I need to set the samples. So I can see that 7 seconds was in this stack, 7 seconds was in this stack, 22 seconds was here. And if I zoom in, I see that these are a lot of threads that are waiting for work. I probably was tracing for 7 seconds, I'm guessing, and then I hit Control-C. And these ones that are larger are a multiple of 7 seconds because it's probably aggregated 3 threads together in Netty server I/O. So it's getting to 21. So here's, again, this is a gritty example. This is what really happens when you do off-CPU analysis, is you look at it and you go, wait a minute, this isn't interesting at all. This is just all the threads are sleeping. I was interested in when am I blocking during something interesting, when like you're actually playing the game. I need a way to exclude all this stuff. I need to exclude all these sleeping threads and only look at the application threads. So if I look at the CPU flame graph, that will give us a big clue as to where that is. So if this is the game over here, I'm in the game when I'm in this thing, like Minecraft server. That's the name of that function. It's really small on the screen. Okay, so let's profile it. Oh, I need to do my JMaps as well. JMaps, off CPU time. So I'm going to be grepping this out of the profile. Now, when I go to generate it now, okay, go back to the other one. That's what it looks like. This is all our sleeping threads. It's not very interesting. I can just say grep Minecraft server. Because the folded format is one stack trace on a line, which is great because I can use grep set and awk, and I can just manipulate it however I want. Bam. Now this is the off CPU time just playing the game, and I can see that I still got a sleep in here, but there's another stack. Oh, it's pretty thin. There we go. I should be grepping for whatever this is. Minecraft server B. So now here's the real blocking time while I'm actually playing the game in between the frames. And so I can see there's some blocking time here, whatever that is. Abstract wrapping, script iterator. We're in object monitor, complete monitor locking. So I've got some blocking there. And this is really like the first time I've browsed through this stuff, so it's pretty cool. So we've got a lot of locks. Monitor lock without safe point check. And so it's telling me how many microseconds are in each of these code paths. This is really awesome. So if I give the developer the CPU flame graph and the off CPU flame graph, they can browse them and find where the CPU time is consumed and where the blocking time is consumed during the application. BPF makes this possible because off CPU tracing is actually really expensive because I'm tracing whenever the scheduler does context switches, and they can be millions of times a second. So you really want the ability to do in-kernel aggregation and in-kernel frequency counts, which is what BPF can do. To dump out schedule events to a perf.data file, which I've done before, you can have a gigabyte per second. So it's not really practical. So this makes it all much more practical. All right, I'll stop playing Minecraft now. Let's look through slides, and I'll go back and do some more demos. Enhanced BPF, also known as just BPF, can do lots of things. It's kind of crazy to explain. It began life by a company called PlumGrid. They were doing it for software-defined networking, and Alexei Sorotoyev came up with it. And that was so that it could handle packets, and then you could define some sort of proxy or router or whatever you want in software, and it would handle it. This is really good. This is really good for us because packets can be very frequent. Packets themselves can be millions of times a second. And so since this was designed from the beginning to handle very high packet or very high event rates, it means it's been optimized. And so we can use it for things like off-CPU analysis and schedule analysis. It's been used for lots of other things as well. Denial of service mitigation, intrusion detection, container security, observability, what I do, BP filter, even device drivers. There was an infrared device driver written in BPF. There's been a number of discussions about BPF taking over everything to the point where it seems that the ability to write a user-defined program and have the kernel run it, and that user-defined program to have more and more capabilities sounds a lot like a microkernel. So microkernels is where you write stuff in user space, and you have a minimal kernel that runs it. And so it's a little bit scary to think about microkernels and Linux, but anyway, I think it was Jonathan Corbett who first came up with that realization that we're heading towards a microkernel. User-defined BPF programs, they go to a verifier, it checks it's safe, and then BPF can attach to socket events, kprobes, uprobes, trace points, and perf events, and whatever. If you're an end user, the BCC repository has lots of canned tools, so you can just use them straight away. I only demoed 2 so far, Profile and Off CPU Time, but there's lots. The tools have man pages, example files, documentation, and usually you can get BCC on a system nowadays just by doing apt-get install or yum install. You need at least Linux 4.4. Yeah, at least Linux 4.4. It's kind of a sliding window because eBPF was added in parts. And there's another front end called BPF Trace, which I was working on a lot last year. BPF Trace is good for powerful one-liners and custom scripts. And so with BPF Trace, I can say BPF Trace, T is for trace point, syscall, sysenter open, print out the file name. Or do a histogram of the read size distribution by process. Things like that. So very nice, very, very simple syntax. And you can write lengthy programs in BPF Trace. I thought I pressed F5. Oh. Shift F5, all right. I can save timestamps, I can do custom latency calculations, and so on. eBPF is solving new things. Off-CPU analysis was this cool thing we really wanted to do, but it was so prohibitive to trace scheduler events. Now eBPF is letting us do it. Another thing it's letting us do is I can save stack traces when a thread blocks. No, I can save stack traces when a wake-up event happens, and I can associate wake-up threads with wake-up stack traces of blocked stack traces. So I can take that off-CPU time example further with Minecraft, because sometimes when you're looking at a lock and you're saying, I'm blocked on this lock, your next question is, well, why? Why was I blocked for 10 milliseconds on this lock? Who was holding the lock for 10 milliseconds? I need to know them. Well, you can know them if you trace the wake-up events. So the kernel has to manage this. The kernel has to, so a thread releases a lock. The kernel then does a wake-up from that thread to the blocked thread. So you grab the stack trace there and you associate it here. Doing that association was something we've never done before in kernel context. dtrace could not do it, but it's something that BPF can do. There's lots of front ends for BPF. Raw BPF is where you write instructions like this, BPF instruction level programming. There's some samples inside the kernel source code. I think very few people are ever going to need to do this. It's really hard. There's also, if you look in the kernel source code, there's C examples as well, which is a little bit higher level. But we've spent years trying to make it even easier. So we've come up with a BCC front end, which has a Python interface, a C++ interface, and a Lua interface so far. And I imagine people are going to add other interfaces to BCC as well, other languages. And so that lets you define your kernel program in C, and then the front end that manages it in Python or whatever that is. With BCC, it's the first time I can put an entire program on a slide. The other ones are way too long. And then there's BPF trace. And BPF trace, I can do a one-liner like this, where it's very simple. I've been updating this slide for a while as things get developed. So BPF trace is now approaching maturity. We're about to release version 0.9. We've been working on API stability. Sysdig just announced eBPF support, which is great. So you can run Sysdig without a kernel module, and it will allow Sysdig to do more. I keep having to bump perf along because perf gets more features in every version. I keep having to bump ftrace along because it gets more features of his triggers and synthetic events. But I've been moving it downwards as well because it's getting harder to use with his triggers. It's getting more powerful. Trace command, but trace command, isn't trace command, well, no, actually it's a front end. So I'm going to have to add trace command, which is, and also kernel shark. I know I should add those. You're right. If you're interested about what trace command and kernel shark are about, I'm sure Stephen will tell you tomorrow. And then on the right, I've got the BPF toolset. So raw BPF, which is brutal to use, and then we get easier and easier and easier. So BCC, a lot of people are developing on BCC. It has a lot of those canned tools. And then BPF trace is the easiest of them all. As an example, just to have one in the slides, this is a BCC tool called biolatency. It's showing the disk IO latency as a histogram. It's efficient. So the count column is what's maintained in kernel context, and it just copies the count column to user space, and user space prints this out. Prior implementations, I had to dump out every disk event and post-process in user space, and that's too expensive. That's the BCC program for biolatency. It's kind of long. Here's the BPF trace version for biolatency. Fits on a slide. Well, it fits on a slide in a way you can read it. So kpro, block account IO start, save a timestamp. Here I'm using arg0 as a unique identifier, which is the block pointer. And on completion, if I've got the timestamp, do the histogram, delete the start one, we're done. So much easier to read than that. That's the BCC version. However, BCC is more powerful because you're in Python for a bunch of this. And so if you're in Python, I can do argparse, I can do socket libraries, I can do whatever I want. And so that's a difference between these tools. BPF trace is great for just hacking up a quick custom tool that does something simple. But once you're like, no, this needs to be an agent, and it needs to support all these, needs to support Google protobufs, and needs to support this and that, then you want it to be a BCC tool, because then you get to use all the libraries. So that's the difference between them. BCC, canned complex tools and agents. BPF trace is great for one-liners and custom scripts. That summarizes BCC for an end user pretty well. You've got all this new visibility into all sorts of different subsystems. And so just to give you a couple of examples, exec snoop tells me what software is running. So if I run Minecraft launcher, let me get out of here, okay. Exec snoop tells me what's happening when Minecraft starts up. So I can say, okay, so that ran, and then it ran this thing, and then it ran these other things. Okay, thank goodness it didn't have my Minecraft password in there, come to think of it. All this stuff. Open Snoop. Shows all the files that are opened. In fact, it's going haywire. It's great for locating config files and log files and things that can help you troubleshoot or debug software. Bash readline, just as a different example, this instruments the user bin bash program every time it does readline. And so it just prints out what was entered on bash shells. I use it because it's an example of user space tracing. But for performance tools, there's things like ext4 slower. I wonder if Minecraft does anything. Oh. So ext4 slower will show slow ext4. Oh, I should be able to do subseconds. It shows slow file system I/O. You can give it a threshold. So I'm saying show me I/O slower than 1 millisecond at the file system level, or I could say 0 milliseconds for everything. Okay, so lots of stuff happening. That's great for proving that there's a file system-based issue before you get down to the disks. Because at the file system interface, you've still got process context, file names, and all sorts of things. Oh, I should run TCP live on Minecraft when I start it up. Or TCP connect. So TCP connect, but there wasn't any from here yet. When's it check my authentication? Let's try TCP live. Maybe it's using UDP? I thought when you started up Minecraft, it went and checked your whether you're authenticated. This is all Chrome. Maybe it's not TCP. Maybe I have to run a UDP tool. Okay. I haven't written them yet. Okay, I haven't written the UDP tools. I haven't written UDP versions of these yet. I should write them. Okay. So anyway, lots of tools. There should be a gap over here. Yeah, there's a gap down here. There's no UDP tools. If you'd like, write some UDP tools so that we can analyze them as well. So anyway, lots of new tools for performance analysis, software troubleshooting, and debugging. BPF trace, there's fewer tools so far that we've published because you're more likely to have custom tools to do various things. This is where BPF trace development is right now. Started in December 2016. October 2018, we were major feature complete, at least for version 1 of BPF trace. We've released version 0.8 so that it can be packaged for Debian. We're working on version 0.9 right now. There's only one thing left to fix. And then we'll get to version 1.0 where at least the known bugs will be fixed. It'll be nice to get to API stability. We're not quite there yet. And so at the moment, I haven't done many blog posts about BPF trace because every blog post I do, I know I have to go back and change the syntax because we are tweaking things. But we're getting close to the point where it will be pretty much set in stone. And so they'll make it much easier to begin to write documentation. But we're not quite there yet. Packaging work has been going on. So as I said, I was in emails with Canonical yesterday about getting it packaged for Ubuntu. The syntax of BPF trace is inspired by many things from the past, like awk and dtrace and systemtap and C. So I've got my probe event, so K, do nanosleep, optional filter, and then an action. So here I'm saying com, frequency count com, which is the process name, and plus plus.
Sorry, can I interrupt you? So I've tried to use BPF trace before, and where I hit problems is I don't know what variables are available to me, where the interfaces for that are. Is it just straight up like, am I accessing kernel structures or like?
So the question is, when you use BPF trace, how do you know what variables are available to you? Because I just used com. I wrote the reference guide. I spent a long time writing this reference guide. And so in the reference guide, there is variables built-ins. And so here's the list. So PID, it's all in there. It's all in the reference guide.
Probably would never find that by searching for PID. So
Yeah, if you search for PID, that's good. So yeah, there it was. Okay. So there is a reference guide for BPF trace and for BCC, and I wrote them both. I also wrote tutorials and things to get you started. Reference guide's really long. You can print the thing out. Different probes that are available. So you can do kernel function tracing, user function tracing, trace points, profiling, hardware events as well. We can access PMCs. We added shortcuts, so you don't have to type trace point the whole time, all the time. You can just do T. Filters use Boolean operators, straightforward. Actions, there's per event output, things like printf and system. There's also time, so you can do custom time strings. And then there's BPF map summaries. So I can say it's the @ represents a map symbol, @ equals count, or just @ ++, @ equals histogram. And as I say in the slides, they're all in the reference guide. And so there's lots of functions. So for doing log histograms, linear histogram, log2 histograms, linear histograms, counting sum, min, max, average, doing symbol resolution, and then working with maps. The variable types, yep.
Does the symbol resolution have any problems with the recent spectrum meltdown mitigations?
Does the symbol resolution have problems with spectrum meltdown mitigations?
Yeah, so there was a lot of obfuscation for the kernel stack. Are you following anything I'm making any sense?
Yeah, so the more...
Crash won't work on proc mem for this reason.
Yeah, more often nowadays, we're booting kernels with the address space layout randomization stuff and the PIE stuff. And we've had to do work in BCC to work around it. And so BPF trace calls into the BCC symbol resolution functions. And there was a while where it was broken because of this, because we were more often doing address space layout randomization. So, yep. If you want to do any security, turn off eBPF. Now, some people are saying that BPF isn't secure, but the thing you've got to remember about security is with BPF is you have to be root to use it so far. So I can't make the BPF syscall unless I'm root, unless I'm caps sysadmin. So like the ship's already sailed, you're root user. What's that? You can... I've heard of people turning off BPF and ftrace because they're security minded, but it's like, I mean, what's the vector? Like, you have to be root anyway to be able to use this stuff. So the ship has sailed, right? We do eventually want to make the BPF syscall usable by non-root users. Okay? When that happens, yes, we have to be, then people want to turn off BPF. There's already a sysctl for it, for disabling privileged access. Right, perf has been through this, and you can look up the CVEs that perf had to deal with, because you can run perf as non-root, of course. But we're already getting prepared for that. So unprivileged BPF disable, you can already turn that on. And some people would say that should be on by default, whatever, fine. Because it basically is on by default now. So in the future, which maybe take like 5 years, there may be non-root BPF access. A big user of non-root BPF access is going to be containers, because people want to run the BPF tools within a container. Right now at Netflix, I log into the host and I analyze containers from the host, but I can't go from the container because it doesn't have cap sysadmin. So there's lots of functions that are in the reference guide. Variable types, basic variables, associative arrays. Built-ins are in the reference guide. I should put that on the slide as well. And so now when you look at a program like BIOS latency, after you've gone through the syntax, it should make more sense. So there's my kprobe of kernel function, save something, completion, and then print it out. If you're not a kernel engineer, you may find it intimidating to go through kernel stuff. You can get a lot of value out of BPF and without ever writing code, just by using the canned tools. And as for writing tools, try to use trace points as much as possible because they're stable and maybe more documented than kprobes in the first place. I drew a picture of how BPF trace worked internally. But that's online if you're really interested. We do go and use BCC, so it does leverage that. And the program gets sent through a Lex and Yak parser, and then there's Clang parsers for trace points and coming up with the structs and semantic analyzers and so on. There's still things to fix. Maybe you want to help out. I want to mention a couple of other tools. At Netflix, we've been working on Vector, and that's our per instance analysis tool. It's open source. And recently, we have added latency heat maps to, it's already got flame graphs. We've added latency heat maps to Vector. I've been adding flame graph, like the off-CPU flame graphs, but so latency heat maps, my colleagues and volunteers have got this in there, which is really great. So like the histograms we saw, or maybe we didn't say because I didn't demo it. So here's my ext4 file system. Oh, what boring histograms. Okay, it's a little bit better. So these are histograms, right? So I can look at like latency distribution in microseconds. Oh, look, it's bimodal, and there's a latency outlier that's 4 to 8 milliseconds. I want to see that over time. I don't want to see that for during tracing. I want to see that every single second. And so that's what latency heat maps allow us to do. I first came up with these like 10 years ago, and it's good to see them start to get used again. And we've been open sourcing that. And I did want to stress about GUIs. I do think most people who use BPF in the future will be using it via GUI, and they probably won't even know that BPF is there. I can go to the command line and demo all this cool stuff, but the SCaLE tool end users is going to be much fewer than the GUI end users. And at Netflix, SSHing onto an instance is a last resort. We have something like 150,000 instances running. Which one do you SSH onto to work on a problem? And so we have to make things work through GUIs to operate at that scale. And so most of the users at Netflix for BPF are going to be using it from Vector, right? They're not going to be SSHing on and doing stuff. They're going to be using that. And Vector also has flame graphs. Like the off-CPU flame graph I just generated for Minecraft, we've automated that as a push button inside Vector. Maybe I could have demoed it with Vector, and then I wouldn't have had to run all the commands. All right. That's the tool users. So yeah, GUIs, there's a lot of people use it from GUIs, and that's fine. If you're going to develop BPF tools, BPF trace makes it a lot easier. So I expect there to be a few thousand people who will be writing custom things for their application environments with BPF trace. There's probably going to be a couple of hundred people who are doing BCC tools, custom agents, because BCC is quite powerful. Remember, BCC, you can use all sorts of extra libraries and interface it to things. So you may look at BPF and say, well, it's great, but at work, we already have this dashboard monitoring tool, and we need to plug BPF into our existing monitoring thing. And so you probably want to look into BCC because it's Python. There's probably a library, so you can connect the dots. I don't think many people are going to write raw BPF or the C interface because we just don't need to. We've got higher level interfaces. Some people will because they'll have some weird reason for doing that. And to mention a couple of other tools, there's kubectl trace for running BPF trace on Kubernetes. And I mentioned earlier, Sysdig have added eBPF support. And we'll see eBPF added to other tools as well. Bless you. So takeaways. You can easily explore systems in powerful new and custom ways. You can also contribute. And also, please, if you can, share war stories and blog posts and give talks about these tools. It's a lot of new stuff. And if you come up with a cool usage, it's going to help the BPF community to share it. I'll publish these slides online. And that's my talk. So I'll take some questions. So while I'm here, what questions do you have about BPF, BCC, BPF trace? Yes?
Last year, same place, same time, you said you were going to work on changing the name of BPF to something more kernel trace buffer type stuff. What did that
So the question was last year, we wanted to change the name of BPF, because BPF is kind of a terrible name. BPF, maybe I should have said it, it stands for Berkeley Packet Filter, but nowadays what we're doing has nothing to do with Berkeley, little to do with packets, and little to do with filtering. And so a better name would be something like Virtual Kernel Instruction Set, VKIS, Virtual Machine. Anyway, Alexi and I are engineers and we're terrible at naming, and we couldn't come up with a better name. And Alexi has settled on BPF because he sees it as, and like he wants it to be BPF and not eBPF because he sees it as equivalent to x86 and ARM. It's like, because it is, BPF is an instruction set. And so this is a virtual machine instruction set. So he wants it to be 3 letters like everything else, x86, ARM, BPF. So that's why we're stuck with BPF. Other questions? Yes?
Is there a place to talk with other BCC computers?
Yes, so every 2 weeks we have an IOVisor concall. So the Linux Foundation project that hosts the BCC and BPF trace repositories is called IOVisor. The name IOVisor is also not a great name because we're doing things more than just I/O. Anyway, IOVisor. And we have a concall every 2 weeks. It's open to the public. And there's an IOVisor mailing list. And so I'm usually on that concall. We spend an hour discussing what's going on, who's developing what. So that's a good place to find everyone. But also the IOVisor mailing list for email. If you look at the IOVisor mailing list, Branden Blanco sends out, when I say IOVisor, I should type it in. So IOVisor, like that. You can see how IOVisor project. So if you just do an internet search for IOVisor mailing list, you'll find the mailing list. Branden Blanco sends out the meeting invite, and then you can join the meeting. Has there been any progress on uprobes in Go? I did some work on this a while ago. I haven't touched it for a while, so I don't know. I have to look up what the current state is. Yes?
I noticed that Red Hat recently announced support for eBPF and tooling. Most of your talk has covered Ubuntu, which I appreciate. What is the state of the tooling in CentOS and RHEL with recent releases?
Okay, the state of the tooling in CentOS and RHEL. CentOS, I'm not actually that sure. RHEL for 7.6 beta and I think for 7.6 official, they've put eBPF for observability into the kernel, not eBPF for networking yet, things like XDP. And they've packaged up the BCC tools. So if you're on RHEL, you can add BCC in whatever RHEL way, and it all works.
How different is their package from your upstream? And if I download your upstream and use it against their kernels or an upstream kernel, is there any compatibilities between their packages and their kernels and upstream their packages and upstream kernels? Are there any compatibility problems going on there since theirs is a fun 310 plus whatever they did to it kernel? You don't know?
I cannot get my head around it still being a 310 plus backports. So surely it's no longer based on 310. Surely it's based on 4. something for this all to work.
But it's stable.
It is stable. Anyway, I don't know. I haven't actually used the Red Hat one yet, so I haven't dug into it. But I'm glad that I'm glad Red Hat have done the support. So.
I'm very glad they did it as well.
Other questions? Yes. Sorry? So I couldn't quite hear, but I think you're saying when I use USDT, I have to specify a process. Okay, so USDT probes, that's user level static tracing, and it's handy because they're a stable API. To use them, however, often you have to specify a -p for process. Now what's great about BPF is I can BPF trace uprobes, bin, bash, readline. Let's do urep probes. my screen word wrapped? And so I can trace all invocations of bash. I didn't have to do a -p, right? That's how a lot of the probes work. We get used to this. It's really fun. But when you're using, in fact, it's in here as well, when you start to use USDT, I have to specify a -p, but I don't want to specify a -p. I just want to do it system-wide like I'm used to doing it. That's really nice. The problem is that USDT probes, if we've got an example, what might I have? What might have it? How about you? Do you have some? So here's some probes. LD has some USDT probes, and so I can go and instrument these. The problem with these semaphores, if they exist, okay, so they're not in use for these ones. So since they're not in use, I should be able to do USDT of this, and then I can do hit start. Oh, this is pretty cool. So I'm actually using USDT right now. So ls just called init start, which is the USDT probe, and I just traced it out of LD. This worked because I didn't have to do -p, because if I look at that thing, the semaphore is 0. So this is why this thing exists. It's this concept of is-enable probes. So these probes have arguments. So coming up with a stable probe is not just about a name, it's about arguments. So if I trace a database, a query, what do you want the arguments to be? Well, I want the arguments to be the name of the database, the user who's logged in, the query string. Okay, sounds good. What if one of those arguments was computationally expensive to instrument? So it's just not available as a C string at that point in the code. You have to go and run a routine to reassemble the string. The problem with USDT points is when you put them in the code, they get compiled into NOPs. And so the NOP gets replaced with the jump to go and do instrumentation. And so it's hard to come up with that more complex argument. So they wrap them in basically an if statement. If this probe is being instrumented, only then pay the tax of doing the expensive computation to coming up with that string. And so then there's the problem of if I'm in my code, how do I know that there is somebody using BPF tracing me? So imagine I'm a C program and I'm running instructions, loads and stores. How do I know that there is out in the universe someone running BCC on me? I'm an instruction pointer, right? They do it by having a known address, and you actually write to memory, and I check that known address to see if it's been flipped to 1 or 0. And if it's been flipped to 1, it's like, aha, someone's watching. So now I'll do the expensive stuff and calculate those arguments. That thing is a semaphore. That's what's listed here. And some of the USDT probes use it. And so if it's semaphore-based, you have to use -p, and then BCC and BPF trace will actually go and flip bits of memory inside the instruction, inside the memory address space of the process, which sounds a bit scary. But hopefully we didn't make a bug or we don't corrupt things. But that's how this works. That's how this is going to work. I mean, all this stuff's pretty scary. We're like dynamically patching instructions live. That's how this all works. So yeah, there's a long answer, but that's why that is. I'll take a couple more questions and we should end. Yes?
In one of the examples, you said you have to recompile with the PO type stuff. What if there are some cases that you cannot do that because sometimes it changes the process timing and you cannot reproduce the same performance?
I had to, for my Minecraft example, it was really good because it was such a pain to get this to work because I had to recompile everything with the frame pointer, right? Now you say, well, what if that's too expensive to run software with the frame pointer? Please check this out and prove that it's actually that expensive, because every time we've done it, it's negligible. It's like less than 1%. There's one case where I've seen that we think it was much more than 1%, and I'd love to analyze it and see what went wrong, but I didn't have PMCs and PEBs, so I can't get a good profile of that. So it should be negligible. It should be not a big problem. We shouldn't have to go through all this pain of like recompiling things with a frame pointer. I would like Debian and Ubuntu to give me libc packages with the frame pointer and libpthread with the frame pointer. Like the frame pointer, it's time to bring the frame pointer back for x86 because it's such a pain to live without it. And so I want to see it turned on everywhere so that we don't have to compile everything. Too many times I've spoken to other companies about how do you deal with it? Like, oh, we just recompile the whole software stack with the frame pointer. It's like, thanks. So everyone's doing the same thing. Like we need to fix it upstream. Last question.
So it sounds like you guys are doing all of your performance. You constantly have all of these things turned on. You constantly have the frame pointer sections turned on for your Java JVMs. Is that correct?
Yeah, we turn on frame pointer for most microservices. Yeah.
Okay, and that's just running all the time.
Yeah, all the time. Yep.
And you've seen no major performance problems as a result of that.
There's only one microservice that had a major performance problem, and they said it was 10%. Now, there's a lot of weirdness about that microservice because they had their stack depth was over 1,000 frames. That's after inlining. This broke Linux perf, so Arnaldo Calvo de Mello went and fixed the kernel. That's actually why we have I can't type. So this is why we have the perf event max stack, this here. This was added because of Netflix's microservice that had 1,000 frame deep stacks so that at least we could start recording stack traces. And if 1,000 sounds bad, that's after Java has inlined it. The uninlined stack trace is 3,000 frames deep. And so this is like an insane application, but they thought that the frame pointer cost was 10%. I'm not sure if I should believe it. What I want is a profile where I can find out why is it 10%. Is it 10% because the extra function prologue instructions? Is it 10% because we're just busting the iCache for some reason? To do that level of profiling accurately, I need not just PMCs, but I need PEBs, precise event-based sampling, because you can't profile the function prologue accurately without PEBs. And PEBs is currently not enabled in the cloud, so I can't do PEBs-based profiling, which annoys me. Until I deploy a bare metal server on EC2, then run the Java stuff there, then I can do PEBs, then I can look at the function prologues, then I can explain why they had a 10% regression. And at the end of all of this, even though they had a 10% regression with enabling the frame pointer, they did it anyway, because the value of CPU flame graphs was more important. They initially didn't for a year, and they had this canary, it was the flame graph API canary, but then they got sick of it, and so they turned it on everywhere.
I feel like I'm going to have to fight this battle.
We're all going to have to fight this battle, I know.
I wanted to hear what you had to say.
I know, it's really, I hate unsolved performance issues. I want my PEBs back so that I can put my finger on, this is where all those cycles are. This is why it was 10%.
That's why I measured, 10% is about why I measured
The
the kernel.
kernel? But come on, the kernel doesn't have that deep stacks.
With frame pointers. Frame pointers had it. Well, no, what about 5 or 6%?
5%, that's still pretty big.
That's why they turn off. RHEL has frame pointers that they turned off.
RHEL has frame pointers. Don't turn frame pointers off. I want frame pointers. How are we going to stack walk? Are you going to write awk in BPF? In BPF?
Orc, yeah. We use the stack on Winder. Orc on Winder is actually how we.
Yeah, you're using awk from debuggers and like the messages, but like how are we going to code awk in BPF?
No, it uses the stack trace, the stack dump uses orc. There's an orc table inside the kernel.
There's an awk table. I know that, but I need to implement that in a BPF program. Okay, we can have a.
Offline.
Yeah, it can be done. All right.
Well, you can join in.
Yeah, we can have a helper. We can have a helper function. Yeah, we can have a helper function and then call it. All right, fine. All right, I'm around at the conference, so feel free to ask me more questions. Thank you very much. Yes, if you're in this room, please see Stephen's talk. It's going to be awesome as well.